were together, I think we were doing some fantastic integration stuff, right? We were doing Ampere's law and all of those good things. We talked about, I want to go back here. Maybe it was up here. I don't remember. There it is. Yeah, so we were looking at this whole concept of trying to find a magnetic field in some sort of highly symmetric situation. And we decided to take, I'm just trying to remind you of what we were doing just so we can kind of get our brains back in, because if I just say, let's do an example, I'm guessing that would not go over terribly well. At least it won't for me, because my brain isn't back in here yet. So we were talking about this thing that they call Ampere's law, and I think I read you the little historical note about, like, why would you want to take this dot product? I don't know, because Ampere was thinking about something that was wrong, and it just happened to turn out in a good way, which, you know, happens a lot in physics, but bless you, bless you. We decided to take, for some reason, the dot product of B dot ds for a little length ds, and then we found, well, we found a couple things. We found out that if you look at a little length and you're looking at the magnetic field that's around it, that the magnetic field and the little length are always parallel to one another. So that's nice. And then we got really excited about this thing called a line integral, even though we know how to do line integrals because it's just an integral and we're just taking it over a line. We're just going to close up that line, which is where that integral with the circle comes in. And we found out that, oh my gosh, anytime you have any closed loop surrounding a current, B dot ds is equal to mu naught times I. Yay! It's very exciting. It's one of those just kind of nice, useful things. We used it to find some magnetic fields, just, you know, of sets of currents, but then we decided to look at a more interesting set of currents, one through a solenoid. So you've got a current going through a solenoid which makes this big magnetic field, this uniform magnetic field through the middle, and that's the thing we really like. Okay? When we're trying to do experiments, when we're trying to have consistent magnetic field, we need something that's going to be constant through a space, and you can do that in a solenoid. We talked about the idea, and this is, I think, where we ended. Does this look a little bit familiar? But maybe not. Like, okay. So in the solenoid, we said that the magnetic fields inside the solenoid itself reinforce one another, so there's a constant magnetic field here. Sorry that this picture is not super bright, but can you kind of see what's going on here? So this is like we've taken a solenoid, we've cut it in half so we can see inside it. So we cut it like that. Okay. The magnetic field in here is just going to be constant. The magnetic field outside is almost zero because the magnetic fields are going to go in opposite directions, cancel one another out. And so now we're going to use Ampere's law to figure out what the magnetic field is inside the solenoid. That's the game. Does that sound okay? Any closed loop is allowed. Let's use a rectangle. Why? Because it's going to be nice. You can use a hexagon if you want. You could use some sort of crazy amoeba-like shape if you want, but this is going to be pretty nice, so let's use it. Okay? So, if we're going to do this, well, then let's just jump in, shall we? In order to find the magnetic field in the solenoid, well, we have to take the line integral of B dot ds, and we know from Ampere's law that that's equal to mu naught times the current. Okay? And that's the current through. And it depends, the amount of current through is going to be dependent on how big our rectangle is. So I guess we made a square, but it doesn't really matter. But does it make sense that if we make it so that it's a integer number of coils, that it's going to be just through, the current in one of them times the number of loops that are inside our square? Is that okay? Kind of like in the pictures that we were looking at earlier. Yes, no? Can you give me some sort of response? Positive or negative? I'm seeing a couple nods and a couple of, I'm not sure if it's just because it's the day before spring break or what. I need some feedback. Yes, no? Thumbs up, thumbs down. Thumbs what?
I don't know.
Okay. Okay, so this is what I'm going to ask. We have got 75 minutes. I need your brains on. Can you do it? After that, it's spring break as far as I'm concerned in terms of physics. I'm not requiring you to do anything over break, assuming we can get through this.
What's the subscript below I?
Through. So it's the current that's going through the loop. So just like, remember we looked at these pictures last time? And we were trying to figure out what had the biggest value for this. Does this look familiar to you? I want to hear some words. Come on.
Yes.
Yes. Okay, good. I'm glad. Yes. And the way we did that was to figure out how much current was going through the loop. Yes?
Yeah.
Yes.
So, yes. Good. So every loop has a different amount of current going through it, right?
Yes.
Yes. So that means that it has a different value for the log integral of b dot ds, right? Yeah. Okay, good. So let's use that idea here. So I'm making a loop. It's a square loop because squares are nice. Okay? Square loop happens to cover, in this case, 1, 2, 3, 4, 5 pieces of coil. Yes?
Yeah.
Hey, right? So instead of writing just the I with this weird subscript that you can't even read anyway, I'm going to say that it's mu naught times, in this case it would be 5, but I'm just going to use a capital N for the number of loops that are going through there, okay, times the current in any one of those loops. Okay? Now, in this case, because I've got a funny square, I can't quite play this game in its nice form, so let's take it one little piece at a time. If I look at this square, and I look just at this top part here, what did we say about the strength of the magnetic field outside the coil?
0.
It's 0. So that means that B dot ds outside the coil is going to be what?
0.
0. Okay, so we've got 0 for that little piece. And then let's look at this little piece here. And think about what B dot ds is going to be there. What's that? I just didn't hear what you said. Okay. So the magnetic field, well, outside it's 0, and right here it's going this way. And so you've got magnetic field going this way, and which way does ds go? So we're talking about this line. So a little chunk of that line goes up or down, right? So you've got, let's take a look at this. Let's think this through here.
0.
I've got a little ds going this way, and I've got a b going this way, and if I dot those two things together, 0. So I've got plus 0. And then let's look at this side. Also 0, right? This is why it's nice and convenient to choose a square in this case. What about the last part? This one down here, is that 0? Because that would be kind of an unexciting question then.
It's B times.
It's b times what? Well, what's the ds if I add up all these ds's?
Just S.
S or the length or the whatever, right? The length of our square. So it's just going to be b times the length of the square that we've chosen. And the only reason I'm using an L is because that's what it says right there. Okay? So if we use that and put it all together, we can say that the magnetic field inside the solenoid, because remember, it doesn't matter how big that loop is, just that it's containing a certain amount of current. That's what Ampere said in his mistaken but lovely law that has come about. We've got mu naught times n times I divided by L. Okay? So this is the magnetic field within a solenoid. Brian, you think of a question?
No, I'm just stretching.
Okay. Is that okay? Okay. So I'm going to put a box around that because that's important. Have any of you guys had an MRI? Has anybody had an MRI? Yeah. Do you know what MRI stands for? Magnetic Resonance Imaging. Mm-hmm. Yeah. And I've never had an MRI. What's it like? What do you do?
You sit on a table. What did I give it? I think it was on my knee. So I was like on a table, and then they slid the table in, so my leg was in there. Then you hear the sound, and it goes like boom, 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 boom.
Yeah, and it's like a big machine, right?
Yeah, it's a big tube.
A big tube. Do you know what that big tube is?
Solenoid.
It's just a solenoid. Like you're just sticking your leg in this thing, right? Okay.
I like this really.
What's that? So in theory, yes,
Okay,
one
you're
could
really
do an
smart.
MRI
It's like a
with
magnet or
it.
something.
So really, what happens is that because in order to make the image, they're looking at magnetic moments of things and watching how things line up. But really, they're just using a solenoid to make a constant magnetic field, right? And then they're looking at properties within that. Okay? So that's really all it is. That's really all it is. Did you know that MRI is not really the name of the machine, and that's not really the name of the technology? It's actually called an NMR. Like if you talk to a physicist, they're going to call it an NMR, which means nuclear magnetic resonance. But the medical community decided that having the word nuclear in the title would not go well for the PR, so they just took the N off, which I think is hilarious since it is nuclear magnetic resonance. That's what it is. I just think it's kind of interesting. All right. So speaking of which, I had like the tiniest little question mark. Fine. I think I didn't get it when I'll make it really big now. Whoa! All right, there you go. So you have a 1 meter long MRI solenoid, and that's really like literally what it's doing. 1.2 Tesla magnetic field. That's not such, is what that should say. Wow, I had a hard time when I was typing this, apparently. I can't write either. Sorry. Such a large field. The solenoid is wrapped with superconducting wire that can carry 100 amp current. Question says, how many turns of wire does a solenoid need? This is a pretty straightforward question. I like it, though, because it really is an applicable thing, right? This is why we use this stuff. Solenoids are fun just to look at, too, but they're really useful in this kind of situation. That's a pretty easy question, I think. What's wrong?
What? We're so hungry in this class.
Oh, I have a banana, and I have almonds. Would you like some? They're pretty yummy.
What's the constant? 10 to the negative 7 times 4 pi.
Yeah, what was
Yeah,
it?
negative
You're on.
seven.
No, it's just 1.257 times 76.
Yeah, so that would be negative 7. 4 pi.
What?
4 pi times 10 to the negative 7 is mu naught. Is that what you're asking?
Yeah.
Yeah. 4 pi times 10 to the negative 7. Those sound like better estimates.
Yes, that sounds like an estimate straight out of your head. Just guess. 9,549.40.
It's like when you have that bucket of jelly beans, right? How many jelly beans are in there? I'm guessing it's exactly around 9,500, 9,500-ish.
That was the best part about Rat Act with O'Bricky is that like we got him into Cyber Chase to show his dog.
Yeah, you told me about
right?
this. Yes.
And there was like the estimation thing, or like yeah. It was
Poor
great.
O'Bricky.
So
Poor
this
guy.
like throughout the entire year, he's like, "How did you get this answer?" Like we estimated the entire year.
Are you learning Pi stuff for Pi Day or something?
I am, because this is the closest date of PIDA that I'll see you. Yeah.
Oh, did you hear Rachel spiel about how bad she is about the MIT thing with Pi Day? How like apparently they used to announce it at like 1:59 on Pi Day, but now since it's Super Pi Day, it's like wait, 3.141.
926.
It's 9.
Yeah, 926. Yeah.
Why is she mad about that?
Because I think
Changing the time now.
They changed the time now. It's like 8
Right,
hours
because
later.
it's better.
No, but
Or earlier.
But for Rachel, that's very irritating.
No,
We're just gonna
it's
walk
later.
outside.
But
Do it in the morning.
We're gonna walk outside with Aaron.
No, but like,
right,
apparently
at
you
that
should
time.
release
Oh.
at 1 in the morning.
Oh.
It's like 9 in the morning.
Got it. That's okay, because that's a much more appropriate time for me to eat pie. So,
Super
Pie is
Friday.
appropriate.
I am excited. No, somebody sent me this shirt, and I was like,
really
if I don't wear it this year, when am I going to wear
For
it?
basketball,
It's
someone
date.
has like legitimately has like a pie day. I would go.
University of
Yeah.
Nebraska Western.
All right, we gotta go.
If I was like a restaurant has a pie day, right?
We digress, and we come back. So one of the pieces that I've noticed very, very strongly when talking about magnetism and electricity to a certain extent, but in magnetism, kind of, you know, when the history of it is presented, and I think it's because magnetism is something that is not intuitive, and it's not something that you see every day, right? Like you see kinematicsy things all the time. We experience and we use magnetism all the time. We just don't realize it. So when they're talking about what's going on in magnetism, they often talk about it in terms of demos and things like that. And the one that the rest of what we're going to talk about today really rests on is the experiment that was done by Ampere. This is the thing that
Wires.
what's that?
And you like wrap a bunch of wire around the loop.
Yeah, well, you're thinking Faraday, I think.
Oh, right.
Yeah, we'll get to Faraday right after
Guys.
break. Faraday's a good guy too. But no, Ampere, I mean, like, I don't really know the whole story here, but the idea that he kind of posited was, if we think about having a wire, so Oersted did this thing, right, where he put the wire and he had the current going through it, and then he put the compasses around it, and oh my gosh, it created a magnetic field, right? And so we're creating something like an electromagnet. We're creating a magnet using current, and that's kind of weird, right? So the idea was here that if you have this wire with a current going through it, and we get our right hands out, and we know that the current's going to the right, then that means that it's going into the page below and out of the page above, right? So we got this thing going into the page, down here, and out of the page up here. And so really, we can look at those magnetic fields, and you know, because you did this in 3rd grade science, or you played with it at the science center or something like that, you've been studying magnets for a long time when you were in elementary school, right? Like that was one of your science units. I have no idea what you actually learned, except that they had north and south poles, and you learned that they repel and attract, right? So anything with a magnetic field is going to repel or attract anything else with a magnetic field. Does that make sense? Two magnets, they can, depending on which pole you put there. So the idea that he came up with, or the concept that he kind of posited was, well, what if I have another current carrying wire that creates another magnetic field? So now I've got two things with magnetic fields, and I know because when I was in 3rd grade I played with magnets and I know that there's some interaction. So I've got something with magnetic fields here that aren't real magnets, they're just wires carrying current, right? But it's the same kind of idea. So his idea here was to say, okay, that if you have any two magnetic fields, okay, they will interact, repel or attract depending on how they're aligned, right? Just as two magnets will repel or attract, right? Okay. So that was the idea. And we're going to come back to that idea in just a little bit and actually look at the current carrying wire part. But I want to make it simple first. I want to go back to the idea of what a current is. What is a current? Movement of electrons, right? So a current is just charged particles that are moving. And so really, if I go back to this little picture here, if I've got one wire that's creating a magnetic field, then really what's happening is that the moving charges in here are feeling a force, right? That's what the interaction really is. It's a force due to that magnetic field. Now let me ask a question. If I turn off the current, will that force still be there? Why not? Because there's no magnetic field, right? Our gut feeling, our experience from when we're in elementary school says that a magnet and a piece of paper, there's not going to be any interaction there, right? It has to be a magnet and a magnet. Or like a magnet and a paperclip. A paperclip isn't a magnet, but it is what? Or it has what? It is, but is every metal going to interact with a magnet? No, it's just a metal that has ferromagnetic properties, right? It's got something in it that's easy to align with magnetic poles, okay? So we have to have something here where we've got two magnetic fields that are interacting. That's kind of the way that we learn it in elementary school. But what we're really saying here is that that charged particle that is moving, and that's the really important part here, okay, feels some sort of force. When in a magnetic field. Okay? So Ampere showed that a magnetic field is going to exert a force on a charged particle. We can quantify that force, F sub B, okay, so the magnetic force, is equal to Q. It's got to be a charged particle. But not only is it charged, it has to also be what? Moving. So it's going to be Q times V, cross product. The other thing that it needs to have, if it's going to feel that force, well, it's a magnetic force, so what does it need to be in?
A mass.
It needs to be in a field. Yeah, I mean, it's got direction, right? Because the velocity has a direction. So it's going to be QV cross B. So we've got a charged particle that is moving in a magnetic field that's going to feel a force. Okay? Sometimes we write this as QVB times the sine of theta, right? That's really what that cross product means. And the sine of theta is the angle between V and B. Okay. We've dealt with this cross product business before. We're going to spend some quality time with it real quick because I want to make sure that it makes sense. So the magnitude is just an easy multiplication thing. The direction we find using what? The right-hand rule. Now, I feel like we talked about this a little bit last semester. I can't remember, though. Did we do it or did I skip it in the book then?
The right-hand rule?
The right-hand rule stuff.
A little.
Okay, like kind of tiptoed around it but not really talked about. Okay, so we're going to do it for real now, okay? This whole idea, so to find the direction, we're going to use the right-hand rule. So here's the thing about the right-hand rule. Number one, you have to use your right hand. I know, I mean, it's kind of part of the name. There are multiple ways to apply the right-hand rule, okay? The whole idea behind the right-hand rule is that you're just making a three-dimensional graph, right? Like you're just making a three-dimensional axis. Now, your book describes one way to do it. It is not the way that I do it. And it's one of those things that once you learn it one way, it's really hard to do it the other way. It's kind of like, this might be an oversimplistic comparison, but it's kind of like tying your shoes. If you learn to tie your shoes in the bunny rabbit loop way, you know what I'm talking about, like the bunny ear, tie him up. That's the way my dad learned to tie his shoes. So that's the way he always tied his shoes. That's not the way I tie my shoes. And I've tried to tie them that way, and it takes like an extra minute for me. Maybe not quite, that might be a little bit of an exaggeration. But it takes a long time for me to figure it out. Whereas if I just do the one loop and go around, then it's like no problem. You know what I'm saying? Like once you learn it one way, it's really hard to do it the other way.
I do it both ways now, though.
Do you?
Yeah. Like I used to do the bunny ears, and recently I've been going to like the loop because it like with the bunny ears it always like right now with my shoe the laces go this way and it kind of pisses me off.
Interesting.
And if I do it the other way, they stay straight.
More information than I had expected to get from that, but there you go. Okay. Well, anyway, for me, tying my shoes is a very similar thing. Maybe not so much for Teresa. I'm going to teach you the way that I know the right hand rule because it works, and that's what I'm comfortable with. Okay. If you have learned it a different way, then use it the other way. That's fine. If you already read the book and you know what they've done and you've been practicing that for ages, then do that.
Yeah.
I don't want to make assumptions, Jack. I don't want to make assumptions. You may have been learning the right hand rule since you were in 2nd grade. I don't know. I'm just going to tell you what I know. So, the way that I deal with the right hand rule, okay? So you got 3 vectors. You've got the 2 that you're crossing, and the order matters, right? You guys, those of you that are in differential equations, linear algebra, you know that if you try and cross them the other way, you're going to get different results.
Yeah.
Right? It's like fundamentally a different deal. Okay? So, order matters. So these 2 things are going to cross and get your result. The way that I set it up in my head, my pointer finger is V. Okay? My other 3 fingers represent B, and the resulting force follows out my thumb. I was about to write that backwards. Don't you guys talk about that as your force? No, that doesn't make any sense. The thumb is the force. Okay? That's the way that it makes sense to me. Again, if you've learned it differently, then go with that. It's totally fine. I blame probably Carlton. It's Carlton's fault. They just decided to teach it to me that way, and that's the way I learned it. So,
is that not like the common way, or is it just like
it's funny because like this textbook does it a different way, and the IB textbook does it a different way. But this is the way that like a lot of people that I know when we talk it through do that. So I don't know. Okay. Because you can rotate it different ways, but there are some ways that are wrong. That's the thing. So you have to, yeah. I know that this way works. Okay, so we're going to try it out. Are you ready? Everybody has to set their pencil down and use their right hand. You're not too cool for it.
I was writing, set it down and use your right hand.
All right, we're going to try this first one together, and then I'll let you work on the others individually. We've talked about this into out of the page stuff, so you understand that, right? So here we go. Let's do this first one together. So the velocity goes in that direction. The B field goes up. So which way is the force going to go? Out of the page. Is that okay? So it's going to feel a force going that way. That's what we're saying. Okay? So I'm going to say out of the page. I'm going to give you the rest of these. There are 5 more for you to work on. So the X's are going into, the dots are going out of. So go ahead and go through those 5, and then we'll discuss them. We'll go through them all. All right. So let's just go around in a circle. Nathan, what did you guys say for B?
Right.
Really?
I just forgot.
To the right?
To the right.
To the right.
Oh my God.
Wow. All right. How about C? Logan, what'd you say?
I said,
You said up. Do you guys agree?
No.
wait, you read C?
So V goes that way.
Wait.
V goes that way. B goes that way. Force goes
Sorry.
up. Wow. Teresa, what did you guys say for D?
What did we say?
I don't know.
Out, right? Is that what we said? I don't remember.
So V is going which
So
way?
B is coming out, and B is going.
Yep.
Oh, so it's going right.
To the right?
Yeah, sorry.
Don't sing it. There you go. Thank you. All right. Pratik, what'd you say for E? That isn't actually marked with an E.
We said. Wait, what did we say?
You can figure it out again.
And it's
So in,
down,
B field,
down.
down. Brian, what'd you guys say for F?
0.
Why?
Because of do the finger pointing away. There, when you point this finger this way, there's nothing coming this way, so there is no resultant field.
There is none.
Also,
yes.
in the equation, it would be the sine of theta, and theta is 180, so it'd be 0.
Yes.
Solid.
Sweet. All right. Going back here, I want to make a point here because this I didn't say it before. It may be implied, it may not, so I want to make sure you know it. The direction is the right-hand rule if you're talking about a positive charge.
If it's negative charge, left-handed?
No. No. I've had students like, oh, I'm going to do that and it's going to be fine. And then I grade that test and it's like 50% right, 50% wrong.
That's actually pretty good.
I mean, right? I mean, it's
That is not bad.
50-50 shot on every single question. So it may be, So here's the deal. If you have a negative charge,
Get those grades with like.
I would strongly no, I'm not saying on the whole test. I'm saying on any question about this. Like, what direction is it? They got 50% of that right. So that's not good. This is my recommendation. When you're reading a problem, if it says negative, underline that or circle that so you don't forget. Use the right-hand rule and then switch your answer. Okay?
I mean, so it's like down, it's up.
If it's down, it's up. If it's left, it's right. If it's
Like it's
in, it's out.
Yeah.
It's like it's up.
Okay?
So basically, look into a mirror. So you get a mirror.
Up is down.
No. Again, you're making it too hard. All you do is use the right-hand rule and then switch the answer.
You can only use a mirror.
No, stop.
So if you're in a
Oh my gosh.
You bring like a mirror to the AP test.
All right.
So you can mirror view the sun.
Try these ones real quick. We have a positive charge moving. It feels a force in the direction indicated. Tell me where the B field is.
Into the page, left.
Right.
Look at the question, Nathan.
Right, that's right. And then this one is in and it's going up. Oh god, this like actually. Oh god.
Wait, that's coming out, right?
Usually when it's like really contorted, then if you just flip your hand over the other way, then it's really okay.
Yeah.
So
It's like you're trying really hard.
going in the
Let's
page.
go out, so we going down. Yeah.
And that one is
What if it was going
So that
in?
would be right.
If it was going in, it'd be going out. But it's coming
I don't even know. That's
Down.
crazy.
right. In, left.
All right, are you ready to discuss?
Yep.
Gabe, start us off. What'd you get for the first one?
I believe I got in.
Into the page. Peyton, what'd you get for the second one?
Right.
To the right? Do you agree?
Yeah.
Don't do it. And Jack? No. Yeah, I skipped you before. Go.
Okay. Down.
Down? Yes? Is that okay?
To the down.
Stop. Oh my gosh. Okay.
It's like middle school over again. Not, I don't know if that's a big flashback.
It's not.
Okay.
Okay. Questions, issues, concerns here? All right. A long wire carries a 10 amp current from left to right. An electron that's 1 centimeter away from the wire is traveling to the right at a speed of 1 times 10 to the 7th meters per second. What are the magnitude and direction of the magnetic force on the electron? This is question 3210 from your book, so you don't need to write down the whole question. You might just want to write down that that's what it is. I'm going to let you work on that for a couple minutes.
What's the equation for a long wire?
Why don't you get an equation sheet out, friend?
Okay.
So what did you get for the force?
Something like 3.2.
3 point what?
2.
3.2?
10
10 to the negative 15?
I got 16.
I also got
16th? 16th.
I got 15.
Okay, wait, what's...
Hey, what'd you guys get?
Did you convert this to meters?
Yes.
Isn't 0.0?
And you use 10 amps, not just 1 amp?
Yeah.
What'd you guys get for
No, wait,
That's exactly
1
what-
centimeter is 0.01
They got
meters, right?
16.
Yes.
I could
Yeah, so I did that.
I also did that.
It should be 10 to the negative 16.
Oh,
Awesome,
That's
yeah!
the right answer. Units are what?
Seniors did something right for one.
Newton.
Newtons.
Just
That just tells us the magnitude. We also need the
direction.
direction, and the answer was what? Up.
Is up.
Is that okay?
You tried
Well,
to
that was a
overthink
joke.
that
I
so
did all
hard.
that.
No.
That actually was pretty funny.
What did he say?
He's like, I did it all by hand, and I thought that was a joke that he was saying. And I was like, oh no,
Did it all by
I
hand.
did it all by hand.
You know that your jokes are good when people think that you're telling jokes when you're really not. Yeah.
Would saying
Well, they're just so bad that-
-3.2 times 10 to the negative 16th newtons down be a correct answer?
I would say, I mean, technically, yes. I wouldn't encourage you to say that because I'm not 100% confident that a grader would catch it and understand the subtlety. Does that make sense?
Yeah.
But yes, it is technically correct. What's up?
If we were solving the problem and we wrote down QVB sine theta and then we wrote the direction was down, and then we plugged in the negative and then we got the negative answer and then we converted it to the answer and then up, would that...
That's fine.
Okay.
Yeah, that's fine. Which is basically what Peyton did. He didn't do the last step, even though he did,
That would
right?
be fine if you did it like that and then you
Yeah.
changed it.
Yeah.
Okay.
So, okay, so here's a weird thing about magnetism that is fundamentally different from gravity when you're talking about something. So if I have a frog and I hold him right here, and I measure the force of gravity on him, I can do that, right? And you could tell me what it is if you knew the mass, right? And the acceleration of gravity, right? And what's going to happen to him? Where's he going to go? He's going to go down, right? And it's just going to keep going down, 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 down. But if you think about this carefully, in a situation like this, I'm just going to come back to this one here. If we've got a velocity, so a positive charge is moving in this direction, it feels a magnetic field this way, or it's in a magnetic field going up, then it's going to feel a force where? Out of the page. If it feels a force, that means it's going to accelerate. It's going to accelerate in that direction, which means that its velocity is changing. So at some moment just a little bit later, its velocity is no longer like this. Now where is it? Like this, right? So then, go ahead and use your right hand again with my pencil that's going out just a little tiny bit. So now V is there, and so now where is it feeling a force?
Like a little bit.
Yeah, kind of like.
So you only have force a little bit over now. To the
A little bit
side.
over, so it's going to go this way. And then where's it going to go?
That way again.
Yes. So what's the motion going to be?
Circular.
It's going to be circular, okay? So when you have a magnetic field and a moving charged particle, it's not going to cause something to move in a straight line. It's going to cause something to go in a circle, okay? So,
It won't be uniform, because isn't the force always perpendicular?
it will be. Yep. So we'll have some nice, I don't know, centripetal acceleration that happens. Yeah, it's coming back. Here we go. I like this graphic. I don't know. I got this from some book. I don't know where it was. It's been a long time ago. But I do like this because it's kind of neat to see. So you've got a charged particle in here. These are just two parallel plates. So I've got a uniform electric field here, right? If I have a uniform electric field, that charged particle is going to move so that it's following the electric field lines. We know that, right? So you've got this like parabolic motion that's going to happen. You have the same kind of situation. You've got your charged particle coming in with the same velocity, but now instead of having a uniform electric field, it's a magnetic field. So the magnetic field, the magnetic field lines here look exactly the same as the electric field lines here. But the force it feels, if you've got a velocity coming out of the page and the B field going that way, it's going to feel a force up, and that's going to cause it to go in a circle, so it's actually going to go out. So it's always going to be perpendicular to the magnetic field lines. Whereas the electric field, it's going to feel a force toward the electric field lines. Does that make sense? So you can actually control where a moving charged particle goes using electric fields or magnetic fields or a combination of the two, and you can actually get it to do some really pretty much you can get it to do anything you want it to do, right? You can basically drive a charged particle wherever you want to just using that information. You do. Before we do this, let's just do a quick little derivation here, just so that we really get this. No, let's do, no, not that one. Where'd it go? This one first. I want you to think this through first, and then we'll do the math. Three charged particles have identical charges, identical masses. They enter a constant magnetic field and follow the paths shown. Which particle is moving the fastest? Which one is moving the slowest? Take a look there. See if you can come up with an answer or reason.
Just number one is the
Number 3 is deeper, for sure.
Fastest would be the one. Why would they have
Just the explanation would be because the force.
Because the force
Just the force is proportional to the velocity. So it'll be a greater force. This will be a greater force for a greater velocity. And the greater force will create, so that's a greater force means that force is equal to mv squared over r.
Okay. Let's play with this a little bit and see. What was your gut feeling? What was your first instinct? Logan, what'd you guys say?
My gut instinct was the biggest curve, radius curve, whatever, is the fastest, and then the smallest circle to the radius was the slowest.
So the velocity of 1 is greater than the velocity of 3?
Yeah.
Okay. And I just wanted to kind of write something up there so that we had something to work from. I heard kind of some murmurings of this comment while I was listening to people talk. Do you agree with that? Do you agree with this statement? So it's feeling a force, just one force, just a net force. It is the magnetic force, and that's causing some circular motion. Right? Okay. So the force is QVB sine theta. We're assuming that the sine of theta is 1, and we're going to keep it in the plane. So it's going to just stay there.
R equals mv.
M and A sub c. What is A sub c?
V squared over r.
V squared over r. So really, we know that the masses are the same, and the q's are the same, and the b is the same. So we're trying to find a relationship between v and r, right? Does that make sense? So let's get the v's on one side, the r's on the other side, and see what happens. So if I have q times b over m, I'm just going to write that all over there because I don't care about any of it, times r is equal to v. Is that okay?
QB is equal.
So the bigger the radius,
The bigger the velocity.
the bigger the velocity. Okay? So were you right or wrong? You were correct.
Trust your gut instinct always.
Yes. Is that all right? Okay. So we use this a lot. This is the place where magnetism comes into play, I would say probably the most in terms of experimentation and also just laboratory equipment. We use this concept of a charged particle moving in a circular path all the time. Not only in physics, we use this a lot in chemistry and in biology, okay? When you use something called a mass spectrometer. Have you guys talked about those in chemistry, biology? I know that they talk about them in chemistry for sure. You have stuff, you have different isotopes, you have different things, you don't know what they are. You need to find out their properties, you need to find out the relationship. So, you use magnetic fields. I meant to retype this and I didn't get that done. I apologize for that. But let's take a look at what this problem says. I'm going to make it a little bit bigger so it's a little easier to see for you.
This totally reminds me of an ACT science question that was on this section 2 years ago.
Because you had to read a big long thing about it and then answer
Yeah.
questions?
No, it was about shooting ions into a magnetic field and seeing the radius with which they circle around.
Boom.
And you actually didn't need to know anything because they just gave you a table.
Oh, see, yeah. But now I'm not going to give you a table. I'm going to actually ask you to do it. So we're just going to make sure we understand all of these words here. Two singly ionized atoms We know what that means, right? Singly ionized means that they are, what does that mean?
Male. They have one E.
They have the same charge, right? Kendra, thank you. I forgot about that. Appreciate it. Two singly ionized atoms move out of a slit at a point S over here in the picture and into a magnetic field of 0.1 Tesla. Each one has the same speed. So you got the same velocity, you've got the same charge. So that would probably imply to us that something is different, right? The mass is different, okay? It says the nucleus of the first atom contains one proton, has a mass of 1.67 times 10 to the negative 27. The nucleus of the second atom contains a proton and a neutron. What is that?
Would that be deuterium?
Yeah, it's deuterium. It's heavy hydrogen, right? So it's a hydrogen with just a neutron. Yeah, yeah. And has a mass of 3.34 times 10 to the negative 27. Atoms with the same chemical properties and different masses are called isotopes. Wah, wah. Two isotopes here, hydrogen and deuterium. Oh, it says it right there. If you just read ahead, then you know. Their distance of separation is what they want to know when they strike the photographic plate here. So they want to know this distance. I bet you can do it. You got to think about it carefully, though. They want to know this distance there.
It's nice that they tell you that it's 2 times so you don't mess up when you subtract the radius.
Yeah, that'd be embarrassing. Because about 85% of people, when they do it, don't see that. That's okay, though. I just want you to get it. All right, give that a shot. What'd you say?
0.246.
0.246?
Is that right? Is that wrong?
I don't know. Did you guys agree?
I didn't do that.
Sorry,
I
that's
wasn't
something
using it.
different, but I probably did something wrong.
Okay, let's figure out what we got for the R's.
Is the charge we use?
What'd you get for R1?
0.01. No.
0.01?
Wait, what?
I'm looking for R1. This value here.
Oh, 4 to 10 negative 13.
I give up.
Okay, hold on, friends. I don't know what. Okay, let's take a deep breath. Let's figure this out. This shouldn't be this bad. So FB equals M A sub C, yes? That's where we're going to start? True or false?
That's true.
True. So this is QVB. I'm going to leave out the sine theta because that's going to be 1, is equal to MV squared over R. We're just solving that for R. So R is going to be equal to QB over MV.
That's what I did. Yeah.
Yes? Q is 1 point, or excuse me.
Well, it would be opposite.
Oh,
reciprocal.
1 over that, sorry. I flipped him over. My bad. Ah! What just happened there? Not what I wanted. There we go. Sorry, let me write that again. So what was it? It should be MV over QB. Sorry about that. So that's going to be 1.67 times 10 to the negative 27 times 1 times 10 to the 6th divided by 1.6 times 10 to the negative 19 divided by 0.1. Right? What do you get for R1?
I got
1.04.
Yeah, 1.04.
0.104 is what it should be.
Okay.
So if you didn't get that, figure out why not, because this should not be a hard thing.
Yeah. As usual, right?
And R2
Just twice.
I didn't get that right.
is 0.209. So you need to find twice the difference between those.
Just the bigger one.
So it's that distance is something like 0.210. Yes? Did you get it? Or is that okay?
Yeah.
Okay.
No, I want. Can we go back up to the numbers?
Yeah.
That must be. I'm getting the same thing. Just wait. That must be added 10 to the 6 where it shouldn't be or something.
Those are the numbers. I just wrote them down because they were kind of small and gray. So.
Can you a little bit farther so I can finish writing down? I just need to write down the last sentence.
Okay.
There we go. Got it.
Got it? Okay. Okay. So, you're welcome. So they use these a lot in mass spectroscopy to figure out masses of things or to figure out charges of things if you know the mass, right? Because if you know the mass and you don't know the charge, you can do the same thing and figure out the charge. Does that make sense? Okay? And how do you know the velocity? How do you figure out the velocity of this thing?
Using parallel velocities.
You use an electric field of some sort, right? And you just accelerate it through some sort of electric field, and then you know if it starts off at 0, you use conservation of energy to figure out how fast it was going at the end, right? That's pretty straightforward too. It's just kind of nice. Another place that they use these a lot, I just wanted to share this with you because it's kind of interesting. They use magnetic fields in particle accelerators a lot. So they use it in things like the Tevatron up at Fermilab and at the LHC. But that's like there are only a couple of those. There are not a lot of those in the world. But they also use these for particle accelerators for cancer treatment. So if you've ever had the whatever of having to kind of think through those choices there, and I have not had a lot of it, but there are different kinds of choices that to help treat different kinds of cancers, and different kinds of treatments work better or worse for different kinds of things. There's things like chemotherapy, which is like actually ingesting things in your body to kill cancer. But then there are also things like radiation to kill cancer, and radiation works very, very well for a lot of things. Usually, when you talk about radiation, what we're talking about is sending photons, okay, or light of different wavelengths into your body to target the tumor. But sometimes they also use particle therapy, and they will accelerate protons and send the protons into your body. And depending on it, again, it's different kinds of tumors react differently, but it's something that's up and coming a lot more these days. And I just thought it was kind of interesting because it's an area that they use this a lot, and it's a very practical one. This thing is called a cyclotron, and there's a little section in your book about it too, but I just wanted to share this with you because I think it's kind of cool. So they have the source of the charges here at A, and then in between where that red stuff is, there's an electric field. Okay, so that electric field is going to cause the charges to accelerate. Does that make sense? Linear acceleration. And so if you start them at A and the electric field, so they flip. If you look up here at the very top, this thing where it has positive and negative, and it has that little whoop, that means alternating current. So it's actually flipping the potential. So we have it pointed this way to accelerate it here. And then instead of having to just run them down a linear accelerator, because that takes a lot of space, okay, then they just turn it around using magnetic field. So right-hand rule says, oh, it's going this way, magnetic field is going into the page, it's going to turn until it gets here. And then the electric field makes it go faster, right? And then it's going to go around, and then we've flipped the electric field now so that it goes across here. Does that make sense? And so it basically just goes through this big spiral. When it's in this space where the magnetic field is, it's not accelerating, it's not speeding up or slowing down, it's just changing direction to turn around. So this is like the U-turn part. And then it speeds up and slows down in this gap. So every time it crosses the gap, it gains energy, it gains velocity. And so then when they come out here, they've got a whole lot of velocity, and they can control how much energy they have so that they can then steer them and send them into the right place so that they can actually help to eliminate the tumor. I just think it's kind of cool. Yeah. And it's a, oh, go ahead, sorry.
What? So why does it flip? Or what makes it
Why does the electric field flip?
Yeah.
So it has to flip because otherwise, so when this particle gets here, a positive charge gets here, it would accelerate across, right? Because it feels the force in that direction. Gets up here, and then, it would just like stop because the electric field would be pointing this way.
Okay.
Does that make sense? So it goes doop, 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 doop. And the cool thing is that it takes the same amount of time to do this one as to do this one as to do this one. So it doesn't have to be just one charge at a time, and we could show that because we don't have a lot of time to do it today. You can show that it takes the same amount of time to go because you're going to go faster around this curve than you're going around this one, right? So you can send a bunch of charges that are all being accelerated at the same time because you can flip this back and forth and back and forth.
How would it change charge? So like that quickly? Wouldn't it be going pretty fast by then?
Outlets flip back and forth, right? This is an AC,
yes,
right?
I don't really know how
Oscillator.
to do that,
We'll get there. We'll get there. Hold on to that. Come back after spring break. We'll do it, I promise.
Yeah, just
But-
don't stay in wherever you're going.
I know, right? Gotta come, yeah. But, so we'll talk about that, but for right now, just know that it's an alternating current, so it flips back and forth and back and forth and back and forth, fast. And they control how strong the electric field is. And if it makes sense, by controlling how strong the electric field is, you're controlling how fast that thing's going. Right? Because it's just conservation of energy. So then you can control how fast you're going to need to flip this back and forth. Does that kind of make sense? If we had more time, we'd go through it, but I don't have time. Is that okay?
Yep.
Kind of freaking out. Okay. Let's keep going. Back to the story of our friend Ampere. He was, we were talking about at the beginning, he was saying that, if you had this wire, then you could have one wire push or pull on another wire, and that's really true. If we come back to the equation that we were talking about a second ago, FB is equal to QVB cross B, which is, that was loud, QVB sine theta. Okay? And we say, but wait, that charged particle, if there are a bunch of them in a wire, we could call that a current. So if we just think about definitions here, we know that I equals Q per time. Or we could write that then as Q is equal to I times time. And we also know that V is equal to some distance over time. So instead of writing Q, I'm going to write this thing. Boom. And instead of writing V, I'm going to write this thing. And putting those together, then I can say that the force, the magnetic force, instead of saying that we're talking about a charged particle, we can say that we're talking about a whole bunch of them going through a wire, a current. I times T times D over T, that's interesting, times B sine theta. Times are going to go away. Is that okay? So then you've got the magnetic force acting on a current carrying wire. Okay, that's a certain length. We usually write that D because it's how far is it going, or I'm going to write that as a length. It's a little vector length cross B. This is an equivalent statement to the one that we had before. It's just when we're talking about two current carrying wires. And so then we can take Ampere's idea literally. We can actually figure out what the force is going to be on a current carrying wire. So let's go ahead and do that. So draw yourself two current carrying wires. I'm going to make mine vertical, just I don't know why, because it seems like the thing to do today. So I've got a current carrying wire. I'm going to call this I1. Oops, it's not very, I'm going to make it wider. Really big wire. And I've got another one over here. I'll call this one I2. And Ampere's claim is that one of those is going to pull or push on the other one. So in order to kind of get our heads around that, we need to figure out what the magnetic fields are going to look like. Talk to me about the magnetic field from I1. What's it going to look like?
It's going to be going out to the left.
Out on the left, in on the right.
Out on the left, in on the right?
It'll be the same thing for I2.
It will be the same because I is in the same direction, right?
Do they have the same current difference?
I'm not assuming that they're the same, so let's say they're different. We don't really know, but we'll just go. Is that okay? So this magnetic field, the one from I1, do you agree it extends out it extends out a long ways, right? The strength of that magnetic field from a current carrying wire, you know, because you just looked it up again when we did that last problem, is equal to mu naught I1. I'm going to call that B1. Mu naught I1 over 2 pi times however far away you are. We'll call that distance D. And we can say then that B2 is, it's the same thing except instead of I1 it's I2. 2 pi D. The distance between the distance between where the magnetic field is being generated from, where that wire is, and how far away you are. Yes.
They're not assuming they have the same.
I'm not assuming they have the same current. Is that what you're asking? Oh, D is the same, right? Because the distance from the center of, I'm assuming a thin wire. I just can't draw arrows and eyes in thin wires. Are you with me there? So if the distance here is the distance between where this magnetic field is generated and where this wire is, that is the same distance as from this wire over here where this field is generated and where this wire is.
That's what D is, the distance between the two.
The distance between the two wires.
Okay.
What do you want me to define it as?
Well, I was thinking like the distance from both, never mind.
Are you sure?
Yes.
You, okay. I don't completely know if I believe you that you're really happy. Okay. I'm just going to keep going then if that's okay. Okay. All right. So if that's the case, so if I say, I'll just write it down. So D is the distance between the wires. Because if you're just dealing with one wire and the magnetic field that it's creating, it's just between the wire and wherever you're measuring, right? Because we did that earlier when we had that one wire in the particle, and the particle was moving a certain distance away. All I'm saying is that I don't want to look at just one, but I could put a particle right there, and then that would be the right distance. Is that okay? Okay. All right. Now, the magnetic field, or excuse me, the magnetic force that number one feels because of number two. Okay, so the force of number two on number one. Okay, the force of 2 on 1 is equal to I times L cross B, where this is I1 and B2. Does that make sense? It's the current in 1 caused by the magnetic field from 2. We can also write that as ILB sine theta, I1LB2 sine theta, and this is the length where they're overlapped, right? So this is I1 L times mu naught, I2 over 2 pi d. Why don't you write an expression for f of 1 on 2?
So what's L?
L is the length of the wire.
Oh.
Yeah.
Can you just explain to me one more time about why it's I1 and B2?
Of course. Here, you mean?
Yeah.
Yeah, so let me go up here for just a second. So the force, the magnetic force that any wire feels is going to be due to the fact that it has moving charges, right?
Yeah.
And the moving charges are in that wire.
Yes.
So that's its current. So this is the current in the wire. And it's not just that there's a current, but that there's a current somewhere near or in a magnetic field.
Yeah.
So this is the magnetic field that it feels.
Of B2. Oh, okay.
That the wire is in. Does that make sense? Does that make more sense?
I think
Okay.
so.
Did you come up with an expression for 1 on 2?
Yeah. I2L.
I2L.
Mu naught over 2.
And what do you notice about those two forces?
They're equal.
Are they equal?
Yeah, they are.
They're equal in magnitude, aren't they?
The current's going to be different.
The currents don't have to be the same because you're just multiplying them together. You've got one here and one here, right? Yeah. So the currents don't have to be the same, The forces are the same. Does that surprise you? It shouldn't, because this is just an example of Newton's third law. That's all this is. Whoa, it's amazing, right? This is just Newton's third law. Okay.
You okay?
I don't think he is. I think his mind is blown in spring break.
It is. So unfortunately, fortunately we got through what we needed to get through.
Yeah.
That's exciting. Unfortunately, these tests are just going to keep sitting here
No,
forever.
I'm good.
Oh, darn.
I'm good.
I hope you guys have a wonderful break.
Spring break now.
Be well. Be safe. Be happy.